After watching this video on the standard addition method, you should be able to compare and contrast the utility of using a calibration curve versus the standard addition method. Plot standard addition data and use it to find the concentration and error associated with the concentration of an unknown, and also design and execute an experiment making proper use of the standard addition method. Standard addition is another method that's a lot like a calibration curve, only it's not. And the math is a little bit more complicated, but it's a really great method for using when the sample matrix is complex or unknown. And it does require a linear response as opposed to just like anything that you can fit of the detector in response to a change in concentration. So, say for instance that you're trying to look for lead in soils. Soils are a pretty complex matrix. There's a lot of other stuff in there, so standard addition might be a really good method. Anytime that you have a bunch of other stuff other than analyte that might have an impact in how your detector is responding to a change in concentration. So essentially what we have here is the ratio of the signal intensity of just X to the signal intensity of just X, your analyte, to your analyte and your standard, is proportional to, or is equal to, the initial concentration of your analyte divided by the concentration of your standard plus the final concentration of your sample. And since you're going to add a standard to your sample, so that changes the final concentration of your standard as well as your sample when you pour. When tasked with performing a standard addition experiment, begin with a series of volumetric flasks. You're going to add the same amount of sample to every flask. Then you're going to add a spike, a variable concentration of spike, which will generally mean a variable volume of a spike solution, a concentrated spike solution, and then you'll dilute them all to this same final volume. Once you have your solutions prepared, then you can analyze them on whatever instrument you have available. After you've finished your experiment, you then need to plot up your data. This data will look similar to a calibration curve, except for that your y-intercept will not be at 0. It's representative of the unknown that has been diluted for standard addition but has not had a spike added. Instead, you read the concentration of the unknown solution on the x-axis intercept, as shown in the red box. But be careful, because there's a dilution factor that needs to be applied in order to get back to the concentration of the unknown in the original solution. So, if the total volume equals the volume of your analyte plus the analyte of the volume of your standard, you essentially have the final concentration of X is equal to the initial concentration of X times V0 over V, and V0 over V is a dilution factor, is called a dilution factor. Same thing for your standard. The final concentration of your standard is the initial concentration times the dilution factor. So this is a version of M1V1 equals M2V2. So in order to calculate the uncertainty, you use this equation where the uncertainty of the concentration of X final is equal to the standard deviation of the Y values over the absolute value of the slope times the square root of 1 over the number of measurements you make plus the average y squared over the slope squared times the sum of xi minus x bar squared. Here are some equations for dealing with the dilution factor, as well as the equations needed for determining the error associated with the concentration of an unknown. Take this opportunity to test yourself by working through a standard addition problem.